Hey, let's get started with our second lecture on PCA. Hopefully today we will end at 6:30 instead of 6:20. If you see me ending at 6:20, yell at me. As usual, PCA is hard. This is a tricky topic, so just keep that in mind. It takes a couple passes to really follow it. So let's continue where we left off last time. I'm going to give you a couple slides to sort of bring you back to where we were, and then we'll sort of continue that derivation, that sort of summarized derivation I mentioned last time. This was a really nice Stack Exchange thread that talks a lot about PCA, a lot of stuff sort of beyond the scope of Data 100, but you might take a look at that if you're interested in learning more. Okay, so remind yourself of this picture from last time. So we have these cloud of points, right? We have this cloud of points, these blue points, and we're trying to identify in those points the direction of maximum variance. Okay, the direction of maximum variance, if we were to draw sort of a football shape around this, is where these pink sort of markers are. That's the direction of maximum variance. We can see that when that line sort of crosses that point, all of those red points are really spread out. The projected points are really spread out. And then those red lines, which are orthogonal projections of those points onto this candidate line, those are as short as possible. The sum of those squared lines is as small as possible. So this is kind of the goal of PCA, is how we identify this direction of maximum variance. We're going to essentially identify that direction with math in a moment. So remind yourself that that direction is called the first principal component. It's the direction of maximal variance in the data, direction of maximal variance. And then we usually express this with a length one vector, a unit vector pointing in that direction. We can decompose that vector into sort of its components. And we can see in this example where we had these two different real features, this rating 1 and rating 2, I had you think about like how somebody might rate a lecture based on clarity and content. We're going to try to construct this like better rating, this single rating of lectures that takes into account both of these ratings. We can see that this first principal component is kind of like a recipe, 0.7 parts of rating 1, 0.71 parts of rating 2, to make this new latent feature 1. Okay, this is sort of our most important latent feature. We also talked about this thing called the covariance matrix last time. The covariance matrix represented by a sigma, represented by this uppercase sigma. Okay, and we saw that on the diagonal of the covariance matrix, we have our variance. So notice in these bottom two plots, if we imagine the x-axis is x1 and the y-axis is x2, these are features. PCA, we don't have any outcomes, there are no y's. We can see that x1 and x2 are uncorrelated. They're uncorrelated, and if there's no correlation, their covariance is 0. They don't covary with one another. So when you hear covariance, you want to think correlation. So this first element, the first row, first column, corresponds to the first feature. The diagonal represents the variance. So we're saying in this covariance matrix that the variance of x1 is 5. The variance of x2 is 1. And then notice the off diagonals are all 0. So there's no covariance. These features are uncorrelated. When we throw correlation into the mix, now we can see x1 and x2 are positively and negatively correlated. We can see that the diagonal elements remain non-zero. There still are variances of these variables, but now we additionally have covariances. We have covariances. Notice the covariances are positive in the left, they're negative on the right. On the left, we have positive correlation. On the right, we have negative correlation. So covariance can be negative. This covariance matrix is going to come into account today. So this is what we constructed towards the end of the last lecture. Okay, lots of moving pieces here, but let me give you sort of the core. So we have this matrix of features X. We have n observation with d features. Previously in the class, we've used like p, like an OLS, to represent the number of features. In this case, we're just using d because of convention. So that's our real data, right? This is our real data, our real features. Our real features. Our goal with this matrix decomposition we talked about last time was to find this reduced form of X. Okay, a reduced form of X that has fewer columns. Those columns are a linear combination of the columns in X. But we're hoping that this reduced form of X with fewer dimensions can express a lot of the variability in X. It can give us still a lot of the information in X, being much thinner. Okay. Now the transformation to go from Z, this reduced form, to a matrix that has the same dimensions as X, we have to multiply by this W transformation matrix. We're going to see in a bit, these rows are called principal components. In Z, anytime you see Z in today's lecture, we're talking about these latent features, these sort of new and improved features that are linear combinations of the original features. And now, how are we sort of framing PCA here? What is this loss minimization actually saying? We're trying to minimize the square distance between each of the row vectors representing the observations. Okay, so that's one vector, and the reconstruction of that row vector, the approximation by multiplying Z, I, the first row of our latent features, and a column in W, okay, or rather the entire W matrix. Okay, we're taking the L2 norm and we're squaring it, sum of square distances, dividing by n. This is kind of like mean squared error, just expressed in a new way. So just like before, we sort of stated our model, we've stated a loss function, let's go optimize it. So let's go optimize it. To make life a little bit easier when we optimize, let's think of the simplest scenario where instead of k features, k latent features, we're just going to make one. Can we just make a single latent feature, a single linear combination of all the features that communicates, hopefully, lots of information about my data set? Okay, can I condense this down to a single column? Okay, and then W will be a single row. Okay, we're gonna have one principal component, we're gonna have one column of latent features. When you multiply these two things, you'll get a matrix that's n by d. That's our reconstructed X. Okay, so our loss function can just be expressed this way. Okay, sum of squared distances between the two vectors. All right, so let's actually run part of this optimization. So how would we approach this optimization earlier in the class? Well, before we had like theta naught and theta 1, we had sort of our loss function as a function of theta naught and theta 1, and we took partial derivatives with respect to theta naught and theta 1, right? We did things in sort of separate dimensions, and you would approach things the same way here. You would take a partial derivative with respect to z, right? You'd set that equal to 0, you'd solve for sort of the optimum equation there, right? And then you'd plug it back in and do the same thing for w. I'm going to skip those steps. So let's assume we've optimized for z, not super important to the intuition for today. Once we do that, we land here, and this is where the last lecture ended. The optimization on this slide becomes equivalent to the optimization on this slide. Once we optimize for z, we end up with a loss function that's just a function of w. Remember, w are our single principal component. Move this over so you can see it. This was our single principal component, our one recipe for constructing our latent feature from our real features. And as it turns out, this loss function can be expressed as the vector w times the covariance matrix. All of a sudden, this covariance matrix pops up in the derivation. You can look at the skip slides to see how it pops up. I just want to show you that it does pop up, and then multiply by the transpose of that principal component. So how do we make this loss as small as possible? Well, we have a negative sign right here. So presumably we want to make w as big as possible. We want to make those elements of w as giant as possible, because then our loss is going to be really small because we have that negative sign in front. But there was a constraint that I mentioned last time where we want to make the w matrix orthonormal. Okay, we want all the rows of w to be orthogonal to one another. In this case, we just have one row of w, so we don't really have to worry about orthogonality here. We just need to make sure w is length 1. So this isn't a crazy constraint. We're just saying make sure w is length 1. Like I said before, we want our principal components to just be a direction. And we'll make it a unit vector. Okay, how do we actually put this into the loss function? We use something called the Lagrange multiplier, again, beyond the scope of data 100. But I want to show you the intuition here. We're going to build it up right on the slide. So the constraint is that WWT needs to be equal to 1. We just need the length of w to be 1. We can introduce this into our optimization by starting with the loss function at the top, and then adding this little random lambda. This lambda is just a scalar value multiplied by our constraint as though it were set equal to 0. So WWT equaling 1 is the same thing as WWT minus 1 equals 0. And we can actually express that constraint in our loss function using this Lagrange multiplier. To give you a little bit of intuition, why that's the case, even if you haven't seen Lagrange multipliers before, again, out of scope for data 100. Now that our loss function is expressed in terms of W and lambda, we would need to take partial derivatives in terms of W and lambda. Imagine taking a partial derivative with respect to lambda. What ends up happening, it's kind of magic. If I take a partial derivative with respect to lambda, there's no lambdas in that expression. Gets treated like a constant, goes away. There's just this single lambda hanging out on the right here, attached to something that doesn't have any lambdas in it. Just like if it were attached to an x and we were taking a partial derivative with respect to x. So if we take that partial derivative with respect to lambda, we just recover our constraint. The optimization just recovers the constraint that we were looking for in the first place. So it's sort of this clever way to include a constraint in our optimization. And you'll see that in the future when you have to do optimizations. This is essential to understanding sort of the part of the derivation I'm going to show you. That's why I include it. So we include this lambda. Now, what would happen if we do the partial derivative with respect to W? Again, vector calculus is out of scope, but I can show you a quick little trick here. So if I were to take the partial derivative with respect to W of that loss function and set it equal to 0, which we're going to do to find the optimal W, we have to do a little bit of vector calculus. Just thinking like sort of casually here, WWT is kind of like the idea of squaring W. Right, it's kind of like the idea of squaring W. What happens if you take the derivative of something squared? The 2 moves out front, right? The power becomes 1, and so the derivative of that WWT just becomes 2WT. Derivative of WWT is just 2WT. Okay, that's sort of the intuition there. Again, vector calculus out of scope for data 100. I just want to show you where we're going. If we set that equal to 0 and then solve, we end up with this nice expression. The covariance matrix of X, and this is like the important expression to take away. The covariance matrix of X multiplied by this optimal W is equal to lambda, which remember is just a scalar, that's just a number, multiplied by this vector. So it's just lengthening that vector. A matrix times this vector WT is the same thing as taking a scalar and multiplying by that vector. What is this? What is this? What is what we just saw? I should have the plot. What is this? What is this a expression of? What is this expressing? Give this a go. See, oh, is the Slido not active? Slido. I don't want this to take up too much time, so let's see if we can quickly get the Slido up. Sarah, can you take a look at the Slidos to make sure the future ones are active? This one's fine, we can just skip it for now, but can you just make sure that the next one is active? All right, so we're gonna skip this Slido just for now. Oh, it's working. Oh, good. Okay, it's just not showing up here. Oh, okay, good. Okay, I'm glad people can see it. Oh, good. No, yeah, I guess for whatever reason the cloud isn't showing up here. Okay, so presumably the biggest thing in the cloud, I don't know if you can see it on your end, is this word eigenvector and eigenvalues. So let's hide the floating meeting control. So what is this? What is this an expression of? So this is an expression showing that W, the principal components, are an eigenvector of our covariance matrix. What does that mean? What does that mean? If I take this matrix and I multiply by one of its eigenvectors, matrices can do all kinds of things like rotating and shearing and stretching. But if I multiply this matrix by one of its eigenvectors, all it does is stretch. It's the same as multiplying that vector by a scalar value. And that scalar value that that vector gets stretched by is called an eigenvalue. Okay? So W is a unit 1, so length, unit, length 1, eigenvector of the covariance matrix. It's an eigenvector of the covariance matrix. Okay, the second sentence is just sort of reviewing what I just said about eigenvalues and eigenvectors. Okay, and so where does this get us? Where does this get us? If we look at the loss at the very top here, if we take a look at this loss, how do we minimize that loss? We said before, we can make that loss really, really small if we make W really, really big. So the loss is minimized when that expression is really, really large. What is that expression the same thing as? Well, the optimal sigma Wt is equal to lambda Wt. So I'm going to replace the sigma Wt with lambda Wt. Lambda is just a scalar. I'm going to move it out front. W is orthonormal. That was a constraint we imposed, so WWT is just 1. And so saying that you want W sigma Wt to be really big is the same thing as saying, well, make lambda big. And so what is the optimal W? It's the eigenvector with the largest eigenvalue. Okay, the optimal W when we're constructing just one latent feature is the eigenvector with the largest eigenvalue. In other words, the optimal W points in the direction of the greatest variance of the data. This is PC1. That is PC1. What is the first principal component? It's the direction of maximum variance in the data, so long as X is centered. Let me pause and take some questions here to make sure that this setup is making sense. Okay, there's a lot of steps going on here. There's a lot of linear algebra. Any questions clarifying this? I'm going to do more clarification slides, but I'll pause here. Oh, what's the question? Where did the Z go? Okay, take a look at the skip slides. Take a look at the skip slides. It's not super, super key to the derivation. That's why for this intuition, you don't have to worry about it. But take a look at the skip slides where we show that when you optimize for Z, the loss function turns into the expression on this slide. It's written up, just so you know. But it's not super important to the intuition here. So that's why I didn't go over that part of the derivation. Other questions? We're going to see these statements a lot throughout the entire lecture, so let's keep going here. Okay, let's go see this visually. Visual intuition, I find, is a lot easier to follow. So what we have here, similar to those pictures before, we have the same data, but it's been rotated 4 ways. So these are identical data sets, same exact shape. I'm just rotating it in different ways. So let's start at the top left. Let's start at the top left. We have this cloud of data. Okay, we have X1 and we have X2. What does the covariance matrix tell us? Well, the covariance matrix tells us that the variance of X1 is 5. This was the same as what we saw before. Okay, and the variance of X2 is just 1. What is the direction of the greatest variance of that cloud? If we just look at the cloud, we can see that that is indeed the direction of greatest variance, just along sort of parallel to the x-axis here. And so our eigenvalue is 5. That's the variance in the direction with the greatest variance. And our eigenvector is the same as this V1, but we just have to make sure it's length 1. So we're dividing it by 5 so that it's a unit length vector. Okay, PC2, what's the second principal component? It's the direction of maximal variance with the constraint that it needs to be orthogonal to the first principal component, which we can see is just parallel now to the y-axis. That variance is 1, and so that eigenvalue is also 1. Notice that the eigenvalues in all 4 of these pictures are exactly the same because the variance in the direction of maximal variance is the same. It's the same data, just rotated. The question is, the covariance matrix changes a little bit, and then the direction of the principal component changes a little bit to accommodate these like correlations that are being introduced. Okay, so that's visually what the previous slide was just saying. So today's big thing now is to talk about singular value decomposition, or SVD. So we're going to connect SVD back to PCA. So we're going to get back to sort of this place using SVD. This is actually how you can compute a lot of these eigenvectors and eigenvalues using Python. So what is SVD? SVD is an important thing from linear algebra. You may have learned it in linear algebra already. You may not have. No worries. If you've never seen the SVD before today, that is totally fine. Just keep in mind, okay, we're not going to explain in Data 100 how the SVD is actually computed. It's going to be sort of like a magic function where you say SVD for some matrix and it gives you the SVD back. And we're not going to explain why it's a valid decomposition. I just need you to take for granted the fact that we can decompose some matrices using the SVD, and I'll show you what that means. So we're really covering the what about SVD. Okay, why does it relate to PCA? How do we get this connection between SVD and PCA? If you want to learn more about SVD, you can check out these course notes, and there's lots and lots and lots of posts and blogs about the topics we're covering today because they are tough and confusing, especially the first time you're seeing them. All right, so singular value decomposition. What is SVD? So it describes a matrix decomposition, so something we talked about last time, but instead of decomposing into two matrices, SVD decomposes a matrix into three matrices. So like before, we start with our matrix of features. These are our features. We have n rows. We have d features. We'll see on the next slide a picture of an example of one of these matrices. I just want to give you the descriptions here. Keep in mind that this matrix has a rank. We talked about thinking through rank last time, right? The maximum number of linearly independent columns. And then we're also going to assume that we have way more data points than features, which is the typical case in Data 100. We want to make sure, we're going to have just a handful of features, right? A handful of columns, but we're going to have a ton of data. We're going to have a lot more data. If that's not the case, SVD changes a little bit. We're not going to worry about that in Data 100. So we decompose X into three separate matrices. U, S, and when you run SVD, you're going to get back V transpose. So today we're going to talk about both V and V transpose. Just keep that in mind. We're going to be talking about both of them. The rows of one are the same as the columns of the other. We'll get you there. So what is U? What is U to start? So U has the same dimensions as X. U has the same dimensions as X. It has n rows, so same count as the observations, and then it has the same number of columns. Okay, the same number of columns as features in X. All of the columns of U are orthonormal. What that means is their unit length. So if I were to compute the L2 norm of each of the columns of U, I'd get 1. Okay, for each of them, and they're also orthogonal. If I multiply the columns of U by each other, they're all orthogonal to one another, so I'm going to get 0. Okay, unlike X. In X, there's no guarantees. It'd be very, very odd for all of the columns to be orthogonal to one another. Right, that would be very odd for everything to be orthogonal, but U, they all are orthogonal. That grayed out fact, not super important for Data 100, but I'm just including it there so you know. S stands for singular value matrix. What is S? S is a square matrix. It's a square matrix. It's D by D. Number of features by number of features. It's a diagonal matrix. So that means everything in this matrix is 0 except for the diagonal. Okay, I have these values along the diagonal called singular values. Everything else is 0 in that matrix. It's a diagonal matrix. And these singular values are ordered from largest to smallest. Largest to smallest. There are R singular values. The rank of X is the number of singular values. If you ever have a giant X matrix that has like 1,000 columns and you're trying to figure out, are any of my columns linearly independent, you could compute the SVD, go count the number of singular values. Okay, this is a way to do it. We could get the rank back this way. And then the remaining values that aren't non-zero or positive are 0. You can't have any negative singular values. Okay, it's going to be positive values in decreasing order from largest to smallest, and then the rest are 0 if the rank is less than D. And then finally, we have this V matrix. It's also square. In this case, both the columns and rows are orthonormal. So if you multiply any row by any other row, you're going to get 0. Multiply any column by any other column, you're going to get 0. And all of the rows and columns are length 1. The important thing, most important thing on this picture right now is this. The columns of V are the eigenvectors, something we've talked about so far, of XTX. What does XTX look like? That looks like the covariance matrix we saw last time. XTX looks like the covariance matrix. So it looks like there is a connection between SVD and PCA. And we might be able to use SVD to help us compute things like principal components. So last time when we defined the covariance matrix, we defined it as a bunch of outer products of the rows of X, okay, summed up over all of the data points. We can shorten that notation by just writing XTX. Notice, this is an important fact, this does not include one part of the covariance matrix. We average over all of those values to get the covariance matrix. So there's a little 1 over n hanging out on the side, but it's a constant. Not going to have to worry about it a lot. But just note, hidden inside of V, okay, we get the eigenvectors of XTX. All right, let me give you some examples to make this a little bit easier to visualize now. So on the far left, we have X. This is like the data we would hand you on a data 100 assignment or a data set that you went out and cleaned. These are the features on the natural scale. We're using that same rectangle data from last time, not because this is something you would actually do with rectangle data, but because it's easier to see connections using this rectangle data. Last time we established that perimeter is a linear combination of width and height. Area is not a linear combination of width and height, but we also reason that area probably doesn't give us a lot of extra information beyond width and height. So we know the rank of this X matrix is 3. At most, there are 3 linearly independent columns, width, length, area. Perimeter is a linear combination of width and height. Now, where does this matrix decomposition, how do we actually get these values? There's a function in NumPy that we're going to use, numpy.linearalgebra.svd, that gives you the SVD of a matrix of features X. And we're going to include this argument, full matrices equals false, because we're using what's called the economy or compact SVD. Don't worry about those details. You can take a look at those EECS notes if you want to know more about what I mean by economy or compact SVD. But typically, the default is to use the economy or compact SVD. And what we get back is a tuple, length 3, that gives us U, S, and VT. So in Python, we can go play with these matrices. So remind yourselves, what is U? U has the same dimensions as X, except all of its columns are linearly independent, and they're also all length 1. Okay, all these columns are linearly independent, and they're also length 1. We have our singular values matrix, where we have the singular values, which are always positive or 0, along the diagonal. Everything else in that matrix is 0. Okay. Notice we have 1 0-valued singular value. The number of non-zero singular values is the rank of X. So like I said, if you ever want to figure out the rank of a matrix, go compute the SVD, count the singular values. And then finally, VT is a square matrix where both the columns and rows are orthonormal. So they're all length 1, and they also are all orthogonal to one another. So that is the SVD, if you just want to see an example of it. Okay, we're going to go play around with it in a demo in just a second here. So let's keep going. How do we actually use this SVD to do something useful about PCA? Okay, PCA with singular value decomposition. So assume that you can construct the SVD. I want you to assume that we have a matrix X where you can construct the SVD. You apply this SVD function, okay, you can get US and VT back. What can you do with that knowledge? So we're also going to assume X is centered. And I'll explain in a little bit why that's important for PCA. Just keep in mind when we defined the covariance matrix in the last lecture, when we made things a little bit easier and sort of removed that minus mu X and minus mu Y, we made them 0. So just note X here is centered. All of the columns of X have their mean subtracted from each value in the column. So what is the covariance matrix? So the covariance matrix is defined as 1 over n x t x. Saw that last time. We're just writing it in more compact form. Let's just turn the crank here. We're going to assume we're able to do the SVD. So all I'm going to do is plug in USVT into this expression. USVT transpose USVT. Okay, we can use our matrix transpose rule where we reverse the order of the matrices being multiplied and transpose each of them. So what do we get? VT transpose is V. We get S transpose and U transpose. We're multiplying this by USVT. We keep going. The columns of U are orthonormal. If I multiply UT by U, I get back the identity matrix. So I get 1 over N, V, ST, S, VT. S is a diagonal matrix. That's nice. It's a diagonal matrix, so I can just multiply all the diagonal values by their corresponding diagonal value. I'm just squaring them. So I can rewrite this as 1 over N V S squared VT. So that's where we land. That's where we land. This is exactly the same work I just wrote, but just explaining each step. We're subbing in. We're using this matrix transpose rule. We're using the fact that U is orthonormal and that S is diagonal. So we can write our covariance matrix as this final expression. Not very exciting yet. Not very exciting yet, but make sure you can follow those steps. Okay, now what can we do with this? What can we do with this? So sigma, we just saw, can be written as 1 over N Vs squared Vt. I'm going to do a little bit of a shifty move here. I'm going to multiply both sides by V. I'm going to multiply both sides by V, and I promise you there's a reason we're doing this derivation. I multiply both sides by V. V is orthonormal. That's just the identity matrix. So we're left with sigma V equals, I'm going to write S squared over N times V. That diagonal matrix I can move around in the multiplication. I can effectively just divide all of those squared singular values by N, and I get this expression that might sound a little familiar. The covariance matrix times a bunch of column vectors is equal to those column vectors multiplied by a bunch of scalars on a diagonal divided by N. What is this? This is exactly what we saw before with SVD. We can connect SVD right back to the derivation that we did with loss minimization. We're able to get there with SVD. And now we can use all of our SVD results with all the knowledge we have about PCA. I'm going to pause here for a moment. Let me just explain what's going on here, and then I'm going to pause. Let me do one more slide here. One more slide. So what are we actually looking at here, just to remind you? It's the same as what we saw before. This lambda was an eigenvalue of the covariance matrix. W was an eigenvector of the covariance matrix. So it's the same idea here. The columns of V now are the eigenvectors of the covariance matrix. And so that means those are all the principal components. All of your principal components are hiding in the columns of V. The columns of V give you your principal components, okay? The directions of the greatest variance in the data that are all orthogonal. Now, what about the S squared over N? Those are our eigenvalues. The singular values over N are the eigenvalues. Those are the variance of the data in each of those directions. So using S and V from SVD gives us everything we need to know about PCA. We have all the principal components, and we know the variances in each of the directions of maximal variance. Okay, this is big. Okay, and we're going to go do this in Python in a moment. I'm going to pause. Questions about this setup? I know we've landed in the same place a couple different times, but it's important to understanding PCA. Questions? Yes? We're just connecting it to exactly the same derivation we saw before. You can just like line up the two formulas. It's S squared over N and lambda are sort of the same expressions here. So lambda was just a single eigenvalue when W was just a single principal component. I'm just showing you how to do it now, where you can get all of the principal components, right, and all of the eigenvalues. And we can express that in this S squared matrix, where we're taking each of the singular values squared and dividing by N. Okay, we'll see it in action in Python in a moment too. Yes, yeah, follow up. It's the eigenvalue of the covariance matrix. Remember, the covariance matrix is 1 over n times x dx. Okay, yeah, that's why the 1 over n is important. That's why it pops out here. Okay, good. Other questions before we start making some pictures in Python? Okay, let's keep going. We are on to a demo, I think, after a couple more slides. So let's actually just see this with some actual numbers here. So let's say I want to construct a two principal component approximation of x. So I have my actual x, I have my actual data. Okay, this is my real data. And I want to try to construct two columns, a two-column vector, or excuse me, two-column matrix that can approximate that x as well as possible, capture as much of the variance, as much of the information in x as possible. How do I do that? Same as what we saw in the last lecture. If I multiply by just the first two columns of V, I'm going to get two latent features. So we have latent feature 1 and latent feature 2. How do we get it? Remember that your principal components are just a recipe. The first latent feature is negative 0.1 parts width, negative 0.07 times height, negative 0.93 times area, negative 0.34 times perimeter. It's a recipe for constructing the latent features based on the original features. Okay, so all of these recipes are hidden right inside of V. And however many latent features you want, we'll talk in a bit about how to choose the number of latent features you might want. All we do to get that number of latent features is just grab that many columns from V in order. Because the first principal component captures the most variance, the second one, the second most variance, and so on. So if you want two latent features, you multiply x by the first two columns of V. If you want three, you multiply by all three columns. Okay, so that's one way to construct latent features using x and V. Now, there's a hidden second way of doing it as well. There's a hidden second way of doing it. So this slide is explaining exactly what we saw on the previous slide. To get the latent features, we are projecting our real features onto our principal components. We saw that visually last time, where we did the projection, where we had the shadow of the points onto our directions of maximum variance. At the very end of the last lecture, there are some skip slides if you want to recall that a dot product can be interpreted as a projection. You can take a look at that for some linear algebra review. Okay, and what we do is we choose the number of principal components we want. Let's say we want two. Very often we want two principal components because plots are two-dimensional. Okay, so we're grabbing the first two columns of V, multiplying by x, and that's giving us our two-column Z matrix. Okay, that's all we just did. This is the interpretation of PCs as a recipe. We start with our original features, and we mix those features according to our principal component recipe to get our new latent features. But using our knowledge from SVD, we can write this. If we know that x is USVT, we can rewrite this as USVT times V. We know V is orthonormal, so we're left with just US. So we can either construct our latent features by multiplying x and V, or by multiplying U and S. Now, XV, I told you, could be interpreted as a recipe of features. How can I interpret US in sort of an intuitive way? So let me show you. So as it turns out, the columns of U are just normalized Z columns. They are the latent features. The latent features are hiding inside of U. Okay? If I were to take this column and normalize it, I find its length, I divide all the elements by the length so that the resulting vector is length 1. That vector is the first column of U. So U are just the normalized versions of the latent features. How do we go backwards? How do we go backwards? We have to multiply by that length. Where is that length hiding? In the singular value. The singular value tells you how to scale up those unit vectors to get them back on the latent feature scale. Important thing to take out of this, there's two ways to get your latent features. You can either take x, multiply it by v, sort of thinking about PCs as a recipe, or you can think about it this way, where you have your sort of normalized latent features. These are our normalized latent features, and we're scaling them up by the singular values. Okay, I know that was a lot of theoretical stuff on slides, so I think we're just about at the demo. I think it's the next slide. Last thing to mention, because we're going to do this in the demo, you might want to go backwards, right? We did all of this approximation where we sort of start with X, and then we decompose it into this reduced form matrix, right? And it's an approximation. How good is that approximation? Well, to test how good that approximation is, I probably want to go transform back into the natural scale of X. And so I can take my latent features and multiply by V transpose. The idea here is we're sort of inverting our principal component recipe, and that'll give us our approximate representation of X. And we'll see in the demo, we can compare visually if our approximation is any good. Okay, so I keep saying demo, we are there. Let's go ahead, do a quick demo. DataHub was having a little bit of trouble with the demo today, so I'm doing it locally. That's why it looks a little bit funky. Okay, so let's go over to the demo here. So this demo, the code is less important here. I'm going to point out when you need to follow the code closely. The most important thing here are the outputs. Essentially, these are just interactive slides. I just want you to keep that in mind. So if it seems like I'm scrolling over code, it's because it's not critical to understanding that part of the demo. I just want you to see a lot of these things visually. So let's go through. We have the rectangle data. This is the same data that we were working with in the slides, where we have width, height, area, and perimeter. Okay. First thing we have to do, we talked about this before, is center the data. Before doing PCA, you need to center the data. We're doing it by hand with linear algebra here. We're going to see in a minute, sklearn can fit PCA in 2 lines. It does the centering for you. But we're sort of going through the steps manually on our own. So I'm taking each column here, and I'm subtracting away its average to get a new centered version of X. So everything's now centered. Another thing that you often want to do in PCA is standardize. Width, height, area, and perimeter are on different scales. Area equals 10 means something different than length equals 10. So I often want to standardize those columns so that if I have area equals 3, that means that the area of that observation is 3 standard deviations above the mean. A width of 3 would imply that it's 3 standard deviations above the mean. So I'm also going to standardize. So we have our standardized X. Let's go run SVD. We run SVD. Okay. Take a look. This is the same as what we saw in the slides. This is an important line to understand. We can use NumPy and the linear algebra module to compute the SVD. So we get back a U, S, and VT matrix. Let me show you what those matrices look like. So U has the same dimensions as X. I'm only printing out the first 10 rows here. So here's U that we've been looking at for a while. It's N by D. There were 4 columns in the rectangle data set, so this thing has 4 columns as well. Okay, the 4 singular values that scale up U to make our latent features, notice we just get back a vector. NumPy is efficient. It doesn't need to give us a big diagonal matrix. There's no need to give us all those zeros. So it just gives us the singular values as a vector. Notice the last singular value here is 0. It's 0. That tells us that this is a rank 3 matrix, which we confirmed on our own. Width, length, and area are all linearly independent. And then finally, VT. The rows of VT are the principal components. The columns of V are the principal components. So we have everything we need to go do PCA now. So let's do exactly that. Just so you know, if you want to turn a vector into a diagonal matrix, you can use this numpy.diag. And it'll give you the singular values as a diagonal matrix so that we can start doing matrix multiplications. So approximations. So we talked about different ways to get our latent features. What are the different ways to get our latent features? One of them is to multiply X by V. V contains our principal components, which remember are recipes for constructing our latent features. So if I multiply X by the first 2 columns of V, I get all my latent features. We can do exactly that here. So remember, NumPy is going to give you back V transpose. In this multiplication, we need V. We are multiplying by the columns of V, not V transpose. So we need to transpose the transpose to get V back. So that's exactly what we're doing here. And then we're grabbing the first two columns and then doing a matrix multiplication with X to get all of our latent features back. One way to get Z, we're multiplying our features by V. V has the principal components, the recipes for making our latent features. And then we can also do it with US. Like I said before, the columns of U are just the normalized columns of Z. We scale them up with S, and it would give us exactly the same values of Z. So I'm not going to worry about this. Let me give you the actual visualization now. Actually, one more thing. So everything we just did can be decomposed into 2 lines. Right? Basically, the whole lecture so far can be summarized by these 2 lines of code. And you might be telling me, well, then why didn't we just learn these 2 lines of code and start learning other things? Well, this is sort of the difference between you and an LLM, right? You can ask an LLM to go do PCA and they could give this code. So if we just taught you this, right, it's like effectively doing the same thing as an LLM. The goal here is to actually understand what's going on under the hood and understand where PCA can be applied. You want to keep that in mind, right? Sometimes you feel like I just want the formula to do this, but this is sort of the thing that distinguishes us from the LLMs at this point. Right, at this point. So we're going to import PCA from sklearn. Just like before, we're going to initialize a PCA model. Right, just like we initialized a linear regression model or a logistic regression model, we're going to initialize a PCA model, and we're going to say, I'm going to want 2 principal components. I want 2 principal components. And then all I do is fit that model. I fit that model directly to X, and notice we get exactly the same latent features that we had earlier from doing a bunch of linear algebra. Okay, so this is doing the same thing under the hood. Notice we didn't have to center X. We don't have to center X. sklearn is going to do that for us, right? But we do have to standardize ourselves. Fortunately, X was standardized earlier in the notebook. sklearn will not do that standardizing for you. Just keep that in mind, okay? Centering is a requirement. Standardization is like a nice to have, okay? Nice to have in most cases where the units are different across columns. All right, so how good is this actual approximation? I mentioned in the slides we can rerun PCA sort of backwards in reverse to get back the approximation of our original data. So let's do that, and what actually happens? So here's sort of our big goal here. Looks a little bit like OLS. Looks a little bit like, let me zoom out here. Zoom out. Zoom. Can you do a zoom out? No, oh, here. There we go. No? Let's see if I can get this in zoom for you. 1 sec. Okay. So we're seeing here our original data is in blue. This is our width, height, and area data. Notice there's a curvature to that data. There's curvature to that blue hyperplane. Right? It's curved. The red dots represent what PCA gave us, the approximation. And you look at this picture and it's doing a pretty darn good job. This 2-dimensional approximation of our 3-dimensional data is pretty darn close. In this case, we were able to represent most of this data with just 2 dimensions. Okay, this is not OLS. Area is not an outcome here. A little bit different. We're fitting so that we're minimizing orthogonal distances to this plane. Okay, I forgot to put a break slide in, so why don't we take a break here, come back in 2-3 minutes, and then we will wrap up PCA with a very cool example from US Congress. Okay? Feel free to come up with questions as well. Okay, let's come back together and wrap up PCA. So we have more demos here. We're going to do one that has to do with the US Congress, and then one that has to do with these interesting images of different clothing items. You'll see what I mean in a little bit. And that'll lead us nicely also into Tuesday's lecture, excuse me, on clustering. Okay, so centering data, computing variance. How do we know how many principal components we need? Why do we center the data in PCA? So a PCA plot is that plot we actually already saw way earlier in the first PCA lecture, where we took this three-dimensional data that had these sort of clusters, and we projected onto a hyperplane that I didn't tell you how to make. Now we know how to make that hyperplane with SVD, and then notice that the two-dimensional representation of that data did a pretty good job of retaining the relationship between those points, even though we lost a dimension, right? We got two sort of new and improved dimensions. And so how do I know if that PCA plot is good? What does good mean? Well, if PC1 and PC2 explain a lot of the total variance, kind of sounds like R squared, right? It explains a lot of the variance. If PC1 and PC2 contain lots of the variance that was in the original data, hopefully the big majority of it, then the PCA plot's doing a pretty good job. Otherwise, it might be omitting a lot of information. So how do we actually express the amount of variance explained by each of the principal components? So remind yourselves what we did last time. We had our original data set, we computed the variance of each of the columns, and we added them up, and we got this total variance. We had this total variance, and our goal was to come up with a representation of this data set with fewer columns that grabbed as much of that variance as possible. And so we did that. We did that. Okay, we did that. We came up with this expression earlier in the lecture. Okay, the component score, what is the component score if I dump this into SVD? The component score tells us the fraction of variance captured by each of the principal components. The variance captured by each of the principal components. Remember before that S squared over N was the eigenvalues, right? The eigenvalues. And what were those eigenvalues? They were the variance in the directions of maximum variance. What were those directions of maximum variance? Those were the eigenvectors in V. So if I just take S squared over N, I have the variances of all the principal components. If I have those variances, I can just calculate the fraction of the total variance that each of those PCs is giving me, right? So the ith component score is the singular value of that principal component, the S squared, divided by the sample size. So I can do that in this case. Okay, I get the singular value, I square it, I divide by 100. That is the variance of the first principal component. That is the variance of the first principal component. If we were to draw our data and draw that principal component direction, the variance of the data in that direction is the value here, 389. And then we can see it decreases. The first principal component explains the most variance out of all the PCs, and it decreases from there. Right? Notice that there's no fourth principal component because we only have a rank 3 X matrix. Okay, so we can see that the first principal component is grabbing like the vast majority of the variance. That one principal component is doing an excellent job, and then 2 and 3 are getting a little bit of variance as well. So quick Slido here. How would we compute the variance ratios? How do we compute the variance ratios? And let me see if the Slido got updated on this end. Okay, I don't think it did. So take a look at this slide for a little bit, and I'm going to put up the Slido in just a moment. How do we compute an array of variance ratios that tell me how much each principal component contributes to the overall variance? Right? Ideally, I'd want to know, like, let's say PC1 gives me 80% of the variance, PC2 gives me 10%, and so on. How would I compute those ratios using the output of SVD? Okay, how would I compute those ratios? And I'll put up the Slido in just a second where you can enter your answer, but think for a moment, how would I compute those ratios? This is an important computation when you're doing PCA. And I can come around for clarifications while you're thinking through this. Okay, so make sure if you haven't already, you might want to copy this down. To get the variance captured by one principal component, you take its singular value squared and divide by n for reasons we saw before. So how do we compute an array of variance ratios? How would we do this? It looks like people have already entered answers, so that's good. Wait a little longer, let folks enter their answers. How would we compute these ratios? Need the variances, need the total variance. We want to get the fraction of that total variance. All right. We're doing good. So why can we just ignore n? Why do we just not even need n? How come we can just get away with squaring the singular values and then adding up all of the squared singular values? So the next slide has a lot written on it, but the message is, I think, less than the text on this slide. So let me walk you through the logic here. So the variance captured by the ith principal component is the singular value squared over n. We derived that earlier. We talked about it before the Slido. If you want the variance for principal component 1, take the first singular value, divide by the sample size. If you want the variance explained by principal component 2, take the second singular value, square it, divide by n. Okay? So if I want the total variance, I could just sum up all of the variances of my principal components. That's the total variance. The fraction of variance from one principal component is just that individual variance divided by the total variance. The n's cancel out. We don't have to worry about the n's. All that matters is the singular value squared divided by the sum of the singular value squared. So this is a nice computation. If you know the singular values of SVD, you're running PCA, you want to get a sense of the variance explained by each principal component, you just run this computation. Okay? S squared over the sum of S squared. Now, what can you do with this? Why is this like variance explained very useful? So using this information, you could make what's called a scree plot. A scree is a geological structure that kind of looks like this out in the wild. Okay, we see this in a couple different contexts in data science, but we can make a scree plot. Scree plot. So this was the statement from before. If PC1 and PC2 explain a lot of the total variance, then the PCA plot is probably doing a good job. It's a two-dimensional representation where we have PC1, PC2, right, the latent features. If not, then it could be omitting lots of information. How do you actually say that PC1 and PC2 are any good? We'll just plot the explained variance. So for PC1, notice the variance explained is 80%. Using just one principal component on that rectangle data set, I can explain 80% of the variance in my data. Okay, using the second principal component. The second principal component gives me a lot less. The second principal component gives me a lot less. And after that, I have diminishing returns. I have that sort of diminishing returns. How do I express that? This is often called the elbow method of choosing the optimal number of principal components. And again, you'll see this in other contexts too. But if you look at this curve, it kind of looks like an arm, right? And the elbow, which is sort of a subjective location, but I like to think where the diminishing returns start, right? The elbow is the point where you're getting as much as you can off of these PCs. Right after that, you're getting a lot of diminishing returns. So in this case, the elbow is right about here. And so you would probably use one PC or the first two PCs. After that, you're not getting a lot of additional information. Okay, that's called the elbow method. There's a lot of subjectivity to it. There are less subjective ways to do it, but this is sort of like the first heuristic you should understand. Okay, one plot to show, and then we're going to do some stuff with Congress data, one of the coolest demos, I think, in Data 100. So this slide, again, we actually saw this in the first PCA lecture. I showed you some data. I showed you a cloud of data that looked something like this, and we looked at this data and we said, well, that looks like the direction of maximum variance, and that looks like the direction of maximum variance that's orthogonal. And then we drew a bunch of nice pictures, and then I had you all turn your heads 45 degrees, and we all discovered that that's just a new set of coordinate axes. And so what is PCA doing under the hood? Well, first, we center our data so that everything is centered around the origin. Okay, so that covariance matrix computation looks nice. And then what does the V matrix actually do? Matrices can perform transformations. V rotates the data so that it's aligned along the axes with the most variance. Okay, this is what's going on under the hood. But we actually did this. We did this visually, right? We sort of realized that this formed a new coordinate system. Now we're just seeing that coordinate system. Instead of having to turn our heads 45 degrees, the slide has turned it 45 degrees for us. Okay, so that's what's going on, right? I just want to show you visually why we're centering first. And now we're on to Congress. So let's talk a little bit about Congress. So what we have is a very cool data set. And you could redo this analysis for more recent months in Congress. But what we're going to look at is the House of Representatives, right? 435 people of the 116th Congress first session. So this is votes that took place in September 2019. You could use the same like APIs that were used to pull this data to go look at more recent votes if you're interested. This is just sort of a demonstration. And what we're going to look at are these roll call votes. Okay, roll call votes are either yay, I vote on the bill, or nay, I don't vote on the bill, right? I say no. So can we use PCA to like uncover relationships in these yay or nay votes without telling PCA about the American electoral system or political parties or how people like to vote or what time they usually vote or any of this? Can PCA uncover patterns of voting in congressional data? So let's go see if that's the case. So congressional vote records. So once again, code in these demos not as important as the outputs. It looks like I'm scrolling over the code quickly because the outputs are the important piece here. So what we have is a long data set with the member of Congress, right? What their vote is, the roll call, I think this is the bill number, what chamber it is, the session. So we're going to make this table look a little nicer. So we're going to make this nicer for PCA. This is the data set we now have. We have all of the members of Congress in that time, or all the members of the House of Representatives at that time. Each column represents a particular bill that they voted on in September 2019. So we have a bunch of zeros and ones, if they voted yes or they voted no. And you might imagine like this isn't just relevant to Congress. This could be a data set from Netflix where the rows represent a bunch of different customers or people using Netflix, and then the columns all represent whether or not they clicked on a particular show, or they hovered over that particular show, or they watched a particular show, right? This isn't just limited to Congress. Keep that in mind, but we're just using it in this congressional sense, and you'll see why in just a moment here. So PCA, what are we gonna do? We're gonna center the data. Again, sklearn does this for us. Let's just do it manually here to remind ourselves. Remember that PCA, or excuse me, sklearn does not standardize by default, but in this case, we actually don't have to standardize. You only need to standardize when the units of the columns are different. In this case, all of the columns are 0, 1, so there's really no need to standardize. Okay, keep in mind before we had area, we had perimeter, right? Different units. In this case, we have a bunch of zeros and ones in every column. No need to standardize. Everything's already on the same scale. But we do have to center. That's always a requirement of PCA. Okay, so we're going to run SVD like we've done before. Okay, we're going to get our U matrix, our S matrix, our VT matrix. And then let's go make a PCA plot. So we make a PCA plot of the first latent feature. Okay, we have the first latent feature here. We have a ton of bills, right? We had 41 bills, I think. There were 41 bills. We've collapsed the dimensionality of this data set from 41 down to 2. We have 2 latent features. Some linear combination of votes on different bills gives us Z1. And then we also have Z2, the second latent feature. And if you're looking at this thing, you can see like there's already sort of a pattern here. We see 2 larger clusters. You might guess in the US Congress, what are those 2 larger clusters? What is PCA maybe picking up on? And we'll see in a moment, but probably the same as your guess. And then we also can see down here that there are these members that seem to be doing something kind of like odd, right? They don't fall in that same 2 sets of clusters up top, right? They all sort of hang out in the bottom of this plot. They're very different on the Z2 axis. And so Z2 is telling me something different than Z1. And so what are they actually telling me? What was PCA actually able to pick up on? So as it turns out, if we modify this data a little bit, and I'm going to go back to the scree plot in just a minute, and we include what party they're in. As it turns out, PCA was able to pick up on different political parties by looking at the patterns of those 0-1 votes. So we didn't tell PCA anything about Republicans or Democrats, but it was able to figure out these sort of differences in voting patterns, and it expressed it in the Z1 axis. So the Z1 axis is communicating in the positive direction how Republican your voting pattern looks like, and in the negative direction how Democratic your voting pattern looks like. Now, what is Z2? We got to think about that a little bit. We see that there's only one green point at the bottom. It's the one independent in Congress. So maybe something different seems to be going on here. But I'll go show you in a moment what this Z2 axis might be describing. But let me go back up for a moment, and let's just talk about whether we did a good job. You know, do these PCs explain a lot of the variance? And so we're going to do that computation that you all figured out in the Slido, where you square each of the singular values and then divide by the sum of squares to get the proportion of variance explained. You can see that PC1 explains 80% of the variance. PC1 alone is doing a lot of work. PC2 is 5%, and then it sort of dips off after that. We can put all that in a scree plot to make this a little easier to visualize. That was the same scree plot in the slide I showed you before. We can see the elbow, just like before, is right at principal component 2. So it seems like one principal component is already doing a lot of damage. Second principal component, sure, could help us out a little bit more. Okay, so this PCA plot is doing a pretty good job. Okay, let's keep going. What else can we do with this data? So one thing you can do, the data is a lot of overplotting, so you can do some jittering. And you'll notice there are some surprising people down here. So Nancy Pelosi in 2019 was the head of the Democratic Party. And let's see if we can get it to show up, but you can see, it's hard for me to get there it is. You can actually see, for whatever reason, Nancy Pelosi, this congresswoman, is ending up like pretty low on this Z2 axis, right? And on the Z1 axis, interesting enough, is on sort of the other side. So something sort of might be going on the Z2 axis that we don't understand. It's sort of beyond Republican or Democrat. So we can dig into that a little bit, and I leave it to you to go dig into this even more. This is like a nice project to think about. So as it turns out, one pattern here, and this would be something you discovered after spending a lot of time thinking about the data. It's not just like magic like this, but as it turns out, if we look at the count of votes across members, so how many bills they actually voted on, we can see that most members of Congress voted on almost all of the bills, all 41 bills, right? Most everyone is showing up and voting a lot. But as you get older, or you're really busy, or you have other things to do, you might not show up as often and go vote for bills. You only vote for the bills that are like really essential, you know, these party line bills where your vote basically decides whether or not it passes. And so we can add, as another dimension to our plot, the number of votes that a particular person had as the size of the points. And we can see that maybe Z2 is communicating a little bit of this. Okay, we can see that a lot of these Congress people down here didn't vote very often. And so it might be communicating the number of votes, but it might also just be that those Congress people are voting so infrequently that there isn't a lot of information for PCA to pick up on their voting pattern, right? It's just seeing like a bunch of zeros, or they don't have many, you know, yeah, essentially it's just seeing a bunch of zeros. There's not enough for PCA to pick up on. Question, yes? So essentially PCA is the sort of like just black and white plot we saw earlier. We're just looking, we're sort of inspecting this data and seeing from the outside that PCA was able to pick up on this information without us telling anything about Republicans, Democrats. Does that make sense? We're sort of investigating what those principal components mean. Yes? That one, sorry. Oh, so number of votes, like you know, again, it's not necessarily number, but it might just be the fact that they didn't vote very often, so it's hard to pick up on the pattern. Yeah, but each PC, remember, is composed of, it's a linear combination of different original features. So it might be communicating information from multiple axes. Okay, there's like a cool linguistics paper that I'm happy to talk about that looked at speech patterns, and they like had people rate different interactions that folks had, and they rated them on different dimensions. They looked at the PCs, looked at the ratings, and then tried to make a sort of lower dimensional rating representation. And they said, okay, well, this like new latent rating 1 is like mostly respect. You know, how respectful was this interaction? And then the PC2 was like mostly formality. And so they took their like 6 ratings and turned them lower dimension. Happy to show you that offline. Okay. We got some time here. We're not going to end at 6:20. We're going to end at 6:30. Another thing we can do is actually just plot the principal components directly. So what we're plotting here is all of the components of PC1. So PC1 is a direction, right? It's a direction in space of maximum variance in this data. So we can plot each of the components of that vector. And each component corresponds to a particular feature. So we can see that bill 515, you know, has a little bit of negative influence on PC1. Bills 516, 517, and 518 have like increasing negative influence on PC1. Suddenly 520 has this like giant positive influence. And so what's going on here? So again, sort of looking from above here, we can go plot the average standardized, the average centered vote. That's why it's on sort of a funky axis. But we can plot the average centered vote by party, where blue over here is Democrat, green is independent, red is Republican. And remember before we said that 515 was a little negative, 516 was more negative, these were more negative, 520 shot up. So it looks like PC1 is like the Republican dimension. How Republican is your voting pattern? Okay, you can see that the same patterns for Democrats are almost exactly reversed. Okay, cool. So Republicans look a lot like PC1. That's why the positive dimension was labeled as Republican. All right, and then another very cool plot from PCA that you should know is called a biplot. A biplot. So what is a biplot? The idea with the biplot is we start with our PCA plot, and then we want to include on our plot some indication of how each of the features contribute to the PCs. So on my plot, I want to have an arrow that says, well, how much does bill 515 influence PC1 and PC2? Earlier, how much does width influence PC1 and PC2? I actually want to think about my original features, because we think in terms of original features, right? We're thinking on these natural scales. The algorithm's trying to get us on this other like new and improved scale. But can we get these natural features on our plot? So if we actually look at PC1 and PC2, this is what we plotted just before, where we looked at all the components of PC1. We actually have vectors like hiding in front of us. We can see in PC1 and PC2, the first element corresponds to the influence of bill 515 on PC1 and PC2. The second elements correspond to the influence of bill 516 on PC1 and PC2. Why don't we just plot these as vectors on our original plot? Let's plot them as vectors. If I just plot those vectors, they're kind of small. We can zoom in and see them. So let's do zoom. I have to do this very carefully. And so, you know, it's hard to line up all the colors. I certainly can't. But we can see that like some of these bills are more closely aligned with party votes. So we can see that these bills were probably all voted on very strongly by Democrats, towards the left of the plot, and very negatively, a lot of nay votes by Republicans, similar to these votes here. Whereas these bills didn't really contribute much to PC1 or PC2, they more had to do with this other dimension. And so maybe they weren't as correlated with having like a strong party line vote. And then again, beyond the scope of data 100, but you can scale those arrows, remember they were so small, in different ways. One way you can scale them is by multiplying by the square root of the corresponding singular value. Don't worry about that for data 100. There's lots of information online about scaling biplots. But if you do that, it becomes a little bit more interpretable on the natural scale of the data. And you might imagine when you're doing PCA with fewer features, you might be able to get even more interpretability here. You're not dealing with like 41 bills, right? We could label them by topic of the bill, or maybe how polarized the topic was, something like this. But you kind of get a sense here of how we can think about feature influence on one of these biplots. Okay, so we have one more demo, another cool demo in kind of a different context for the last 4 minutes here. So this one's cool. So the MNIST dataset is this like very common canonical dataset of a bunch of pictures of the digits 0 through 9 represented as like pixels. How, it's black and white, like how much pixelation do you have at each pixel in the image to create some number. And then using that, you can fit different kinds of models and test out different approaches to categorizing each of those images as, well, this looks like digit 0, this looks like digit 5, and so on. But this data set's really cool. It was constructed to be sort of similar to the MNIST data set, but instead they use different articles of clothing. They use different articles of clothing. So notice we don't have pictures of digits. We now have pictures of dresses and coats and t-shirts. Okay, where each sort of point here represents, you can see this color is like higher when it's a darker point, and it's lower when it's a wider point. Or excuse me, it's higher when it's a wider point and lower when it's a darker point. Excuse me. Okay, so we now have like a representation of pixels for each of these images. Okay, and these images are I think 24 by 24. Okay, but what we're going to do is actually unroll, or 28 by 28, excuse me. We're going to unroll those images into vectors. So we have a 28 by 28. I'm just going to take every row and make a really, really long vector, 784 elements. And so what do we have now? The 5,000 are 5,000 pictures of clothing items. The 784 are features, basically just saying what's the pixel value in each of those slots. Okay, so all we're passing to PCA is a bunch of pictures and just the pixel values. We're not saying anything else. Can PCA pick up on patterns in this data set? So we run PCA, okay, we can see that, oh, it's pretty good. Our first principal component gets about 30%. The second principal component gets about 18% of the variance, third principal component 6%, and we've hit our elbow. So in this case, it looks like 2 or 3 principal components would probably be a good idea to grab a lot of the variance. Not quite as much as we did before, but still pretty good. So if we look at this PCA plot of the latent 1 feature and the latent 2 feature, what do we see? Big cluster of points. Okay, we can see there's like some density around here, some density around here, little density in the middle. But it's hard to sort of see any patterns as sort of humans here. So let's do that same thing we did before and like go label these points by like actual fashion item. So if we label this by fashion item, PCA actually picked up on these different clothing items. It looks like PCA clustered, you know, all of the, are these trousers? Yeah, trousers kind of together, picked up all of the sort of sneakers together. It actually like picked up on some of these differences that were encoded in the pixels. We obviously couldn't encode those differences looking at 784 columns like that, but PCA was able to pick up on the patterns such that it can take 784 different columns of pixel features, take it down all the way to 2 dimensions, and still communicate differences between each of these clothing items. It was like picking up on differences in those images. And then we can do it in 3D too, and get this like cool like brain sort of picture here. And we can see the third PC dimension actually matters here. But we can see like these clusters are also sort of existing in 3D. And we get this like nice pretty picture. Kind of cool. Okay. All right, I'll just quickly go back to the slides just to give you a quick summary. This just explains biplots. You can check this out offline. So just keep in mind for PCA, how can we sort of show our knowledge from PCA? How can we communicate this information? We can use a PCA plot, this 2D plot, a scree plot to tell us all about how good the principal components are, and then finally a biplot, which just goes directly on the original PCA plot to tell us about feature influence. So that wraps up PCA 2. That's my last full lecture of Data 100. We will see you next week for clustering and the final lecture. Have a great weekend. See you next week.